Welcome to the first lesson of Algebra 2 Trigonometry. And we are starting with absolute value equations and inequalities. We don't do a lot of reviewing of what you supposedly learned in Algebra 1. Certainly don't take extra days to do that, but I will try to review some key concepts along the way. Normally I'll start with a slide like this that'll tell you the topic, the section in the book that it comes from, the objectives that are mostly taken from the SOLs, the SOL numbers, if you cared, and when I think that we'll have quizzes or tests. And there's 2 dates given because I have classes on A day and B day. And these dates I'm not quite sure of because I'm not sure how much we're going to get to on the first day, or whether there'll be any other interruptions to the schedule because it's the beginning of the year. And, if I have to, I'll change those. But that's right now when I think we're going to have our quizzes and tests. Now, on to the lesson. From Algebra 1, you should already be familiar with, if not expert, in linear equations and linear functions. So let's review for a minute. What do we mean when we say that a function is linear? Now, and I'm pausing for a second. Normally I make these recordings in front of the class while I'm teaching. Today I'm not doing that because I'm doing a test to make sure this works. But remember the difference between an expression, an equation, and a function. An expression does not have an equal sign. An equation has an equal sign. And a function has a y equal sign. Okay, so expressions are things that we can simplify, right? An equation is something that we can solve, and functions are something that we can graph. If you graph a linear function, what is the shape of the graph? And the answer is, it's a straight line. That's why we call all of these things linear, because if you graphed the function, then the graph is a straight line. Now, when you're looking at an equation or an expression, and you want to know, how do I know that this would be a linear equation or a linear expression? You look at the power of the variables. And if the power of the variable is 1, there's only one variable and it's raised to the first power, then you would say that's linear. So linear means that the variable raised to the first power. Okay. And again, for a function, again, variables raised to the first power. Actually, this variable is raised to the first power too, and we know that the shape of that thing is a straight line. Think of it like y equals mx plus b, right? Slope-intercept form of a line. Okay, what does it mean that we say that it's a function? Well, a function means that this is something like y equals 2x plus 1, that for every x value, right, for every x value, there's only one y value. Now, if it's you did this in Algebra 1, sometimes you did it by looking at a mapping diagram or a set of ordered pairs or a table of values, and in that case you always looked for repeated x values to be the sign that that was not a function. But when you looked at the graph of an equation, of a relation, what is it that what test did you use to tell whether or not it was a function? And the answer is a vertical line test, right? So we're talking about linear functions here. Vertical line test is how you check to see if a graph represents a function. If a vertical line crosses in more than one place, then it's not a function. When it comes to straight lines, all straight lines are functions except for one. What kind of a line is it that would not be a function? And the answer is a vertical line, right? A vertical line, if it goes straight up and down, then obviously it would fail a vertical line test. And in this class, we're going to learn about lots more kinds of functions, right? In fact, in this first unit, we're going to touch on both absolute value functions and quadratic functions. But we will add to this, and this is really the strength of what we do in this class, a whole bunch more that'll be useful to you as you go up the math chain or in your science classes that sometimes use these kinds of functions to describe real-world processes, right? So I'm not going to bore you with the whole list, but this is not saying this is everything we do in this class. This is just the stuff that's related to functions. There's some other sequence and series and probability and statistics stuff that we do near the end of the course. Okay, another review. How do absolute value symbols work? Right, if you put a positive number in absolute value symbols, what's the result? Okay, the answer is it doesn't do anything. Right, the absolute value of 4 is 4. Okay, what's the absolute value of -4? Okay, the absolute value of -4 is also +4. So when you take the absolute value of a number, it's really telling you the size of the number. Sometimes we'll say it's the distance from 0 on the number line. In the end, positive numbers can be a directed distance in one direction, and negative numbers can be a directed distance in the opposite. You don't care whether you're going east, west, north, and south. If you're going 4 miles, you're going 4 miles, and that's it. So just recall, what does it mean, these absolute value, these straight brackets? Okay, now we're going to get into the meat of this lesson, which is how do we solve absolute value equations and inequalities? And we're going to start with absolute value equations. And these are some basic steps. Okay, the first step is, if you're given an absolute value equation in which there is more than just the absolute value symbol on one side of the equal sign, you need to isolate that absolute value expression. Like here, I would subtract 2 from both sides so that it says the absolute value of x minus 5 equals 7. Right? So you don't move on to steps 2, 3, and 4 until you've isolated the absolute value. Step 2. Okay, we're going to rewrite now this relationship into 2 equations, neither of which has absolute value. We can say this same thing without using absolute value symbols. Okay, so the first instance is, what would happen if you take the absolute value of x minus 5 and x minus 5 is actually positive? Right? What are the absolute value symbols doing to x minus 5 if x minus 5 is already positive? And as we saw on the last slide, the answer is nothing, right? So we could just, one of the equations that we're going to use here is going to be x minus 5 equals 7. Okay, what if x minus 5 is negative? Well, then the absolute value symbols are going to flip the sign. They're going to make it the opposite, to make it positive. So it would be okay if x minus 5 equals 7, that's our first equation, but it would also be okay if x minus 5 equals -7, because if it does, when you take the absolute value, it equals 7. Now these two should be tied together with the word or, because we're going to get 2 answers here. And the answer to the equation could be one or the other. Okay, so we isolated, we wrote our two equations. Now we're going to solve them both. And both of these are pretty basic algebra equations, right? Add 5, x equals 12. Add 5, x equals negative 2. So the answer is x equals 12 or x equals negative 2. Okay, now checking the answers. What does it mean to check your answers? Right, that means you're going to take these and you're going to plug them in here, right there. And you're going to see whether that leads to a true statement. If it does, then it's correct. So without having to rewrite it, let me just talk through this. 12 minus 5 is 7. The absolute value of 7 is 7. 7 plus 2 is 9. Check. Okay, negative 2. Negative 2 minus 5 is negative 7. Absolute value of negative 7 is 7. 7 plus 2 is 9. Check. Okay, now we can graph these. And the reason I'm going to do this, because I'm not really keen on graphing these, is it does kind of explain what we did here. Okay, we have negative 2 and positive 12 were the answers. Right? We started with, actually we isolated x minus 5 equals 7, right? So, where am I at? So 5 is the middle of the interval. Okay, that's coming from there. And the answers were each 7 to one side or the other. Okay, that's what this equation represents. It's saying find the solutions that are 7 away from the middle of the interval, which is 5. Okay, now this is what I call a U-try. In a U-try, you try. And this is part of the classwork that we have every day. I expect that you are doing every one of these. If you're sitting on your hands not doing anything, then you're not going to get credit for the classwork, or not all the credit for the classwork. Right? This is where you get a chance to do what I just showed you how to do. And if you don't get it, I can help you. Right? So let's remember our steps here. You should have them written down. The first step said to isolate. Okay, I should have said, since I'm making this recording, and you may be watching this at home, at this point pause the video and you do the problem. And when you're done, then you hit play again. Okay, I'm going ahead now. Isolation was already done. I'm going to write two equations. Either x plus 2 equals 7 or x plus 2 equals negative 7. Those are the two equations. We broke it down. Neither one of those has absolute value symbols. If you write absolute value symbols there, you're wrong. Okay? You're wrong. Don't put them in there. You're going to lose serious points. Solve both equations. Subtract 2, subtract 2. X equals 5. Subtract 2, subtract 2. X equals negative 9. Right? Or, now we can check. Right? If I plug in 5, 5 plus 2 is 7, so the absolute value is 7. If I put in negative 9 plus 2 is negative 7. So that's good. Check and check. Okay, try this one. Again, if you're doing this at home, hit pause now. And when you're done, hit play. Okay, again, on this problem, there's no isolating to do, so I write my two equations. 3x minus 2 equals 13. 3x minus 2 equals negative 13. Solve. Add 2. 3x equals 15. X equals 5. Okay, add 2. 3x equals negative 11. x equals negative 11 thirds. Or, okay, now you can check these answers. I'm going to assume that they're right. How's that? What would you say if I tried to check it and it didn't work? Okay, you'd tell me that it was the wrong answer, and that would be correct. If you plug in your answer and it doesn't work, then it's not the right answer. Okay, but when we start working with some of these other kinds of functions, not just absolute value, but including absolute value, that's not always the case. Sometimes you plug in your answer and it doesn't check, and it's not because you did anything wrong. Right, so here's an example. All right, what's different about this example than the ones we did before? Right, the answer is, in this problem, you got an x on the other side of the equal sign, outside of the absolute value. Right, I'm still going to set it up the same way. Right? 2x plus 12 equals 4x. Now I have to say 2x plus 12 equals the opposite of 4x. Right? It's not necessarily negative, because what if x is negative? Then it's positive. But you're still taking what's ever inside the absolute value equals the right-hand side and the opposite of the right-hand side. Now solve both of these equations. Okay, we got x's on both sides, so I'm going to subtract 2x. Subtract 2x. Right, 12 equals 2x. So x equals 6. Okay, how about subtract 2x? I have 12 equals negative 6x. Divide by negative 6, x equals negative 2. Okay, so now we need to check. That's where this fourth step, check your answer, is important. And it's only really in this kind of equation where you've got x's inside the absolute value and outside the absolute value. Okay, so now let me check on this 6. If I plug in 6 for x, I'll get the absolute value of 2 times 6 plus 12 equals 4 times 2. Oh, 4 times 6, sorry. So that's the absolute value of 12 plus 12 equals 24. The absolute value of 24 equals 24. And that is a check. Okay, let's try the other one. The absolute value of 2 times negative 2, that's up sloppy, plus 12 equals 4 times negative 2. The absolute value of negative 4 plus 12 equals negative 8. The absolute value of 8 equals negative 8. Okay, that is not true. Okay, when that happens, we did everything right. We split it into two equations. We did the basic algebra 1 here to solve. We got our two answers. Everything we did up to then was right. But that answer doesn't check. So that's called extraneous. And an extraneous solution is not a solution. But that's why it's important to check your answers, especially when you've got an x value which is outside the absolute value. Okay, so you go ahead and try this one. And hit pause if you're at home doing this, and when you're done, hit play. And I'm going to go ahead. This is 2x plus 5 equals 3x. 2x plus 5 equals negative 3x. Subtract 2x, we're going to get 5 equals x. Subtract 2x, we're going to get 5 equals negative 5x. So x equals negative 1. And that's an or. So one or the other. Okay. Now if I check, and I'm not going to write them all out here this time. Let's put the 5 up here. 2 times 5 would be 10. Plus 5 is 15. So this is the absolute value of 15. And this is 3 times 5, 15. Is the absolute value of 15 15? Yes, and that's a check. Okay, if there's going to be an extraneous solution, it's probably this one right here. And here's what I'm going to do. I'm going to take this negative 1 and I'm going to put it right there, only on the right side. Right, what am I going to get? What's 3x equal if x equals negative 1? Right? That means this equals negative 3. Is there any way for an absolute value to equal a negative number? No. Right? Absolute values always produce positive numbers. So I don't really have to check what's on the left-hand side. There's no way it's going to equal negative 3. So this is the extraneous solution right there. Right, which means that the only solution is x equals 5. Okay, go ahead and try this one also. Pause. Okay, this is 4x. I mean, the important thing about showing this one is what it looks like when you set up these two equations. 4x minus 1 equals 2x plus 9, right? You take whatever's inside the absolute value, you set it equal to the right-hand side. And next, you take whatever's inside the absolute value, and you set it equal to the opposite of the right-hand side, which is negative 2x minus 9, right? It turns both of those negative. So make sure if you've got more than one term that you remember to do that. Okay, now we can solve. Subtract 2x from both sides. 2x minus 1 equals 9. Add 1. And divide by 2. Okay, so add 2x to both sides. Subtract or add 1 to both sides. Divide by 6. Right. Now, negative 8 over 6 is a fraction, which we should simplify. Okay, in this class, it is not 100% correct if you don't simplify a fraction. Right? What does this simplify as? Negative 4/3. Okay, don't turn it into negative 1 1/3. Okay, we rarely use mixed numbers like that. The higher you go in math, you're more likely to just keep it as an improper fraction. Okay, so let's see now. In terms of checking answers, I got to, if I plug in 5 on the right-hand side, I'm going to get 2 times 5 plus 9. That's 19. Okay, at least it's positive. On the right-hand side, on the left-hand side, 4 times 5 is 20 minus 1 is 19. So that checks. Okay, let's try this one. 2 times negative 4/3 plus 9. Okay, that'll give me negative 8/3. And then in order to add to 9, I need to turn 9 into thirds. That's 27/3. Which is 19/3. Okay, well, at least it's positive. So now we need to check the other side. 4 times negative 4/3 minus 1. Okay, that's negative 16/3 minus 3/3, which is negative 19/3. And when you take the absolute value, that is positive 19/3, and that checks. So in this case, we didn't have an extraneous solution. So you always have to check. Okay, now we're going to get into the absolute value inequalities. Okay, and there's two kinds. There's absolute value greater thans, and there's absolute value less thans. So first we're going to do this, we're going to do absolute value greater thans. And I say that it means greater than or equal to. Okay, we still need to isolate both sides. For an absolute value greater than, we're going to rewrite as two inequalities without the absolute value symbols. And to be proper, I should have said not expression, but equation. Oh, actually it's an inequality. Rewrite the absolute value inequality as two inequalities without absolute value symbols. And then we're going to solve them both. And then I'm not going to say check your answers, because it's kind of hard to check an inequality like that. But you always graph these things. So we need to do that. So if you want to take a second and write these down, and when you're done, go on to the next slide. I'm going to go ahead. So what did we say? First we isolate. In this case, the absolute value is already alone, so I don't need to do anything. And then I need to break it down into two different inequalities and no absolute value symbols. So again, we want to write two inequalities which say the same thing as this absolute value inequality, but don't need absolute value symbols. All right, so what is this telling us? Again, if I take the absolute value of a positive number, then it stays the same. It doesn't change the value. Well, if this expression inside the absolute value, then if it's already greater than 13, and it's positive, therefore, then the effect of the absolute value is nothing. So basically, if our expression is in this zone right here, right, to the right of 13, then it's good. So that's going to be one of our inequalities. 4x plus 5 is greater than 13. Right. But it would also be okay if 4x plus 5 is less than negative 13, meaning to the left of this, then what's going to happen when we take the absolute value of it? Right? It's going to take the value and it's going to flip it so that it's up here. So actually we're okay if our expression, whatever's inside the absolute value, is either greater than 13 or less than negative 13. Right? Because if it's less than negative 13, when you take the absolute value, it is greater than. So let me write this as 4x plus 5 is less than negative 13. And those two are connected. This is a compound inequality, which means there's two different inequalities, and the word that joins them is or. And you're not correct if you don't have that word or there. You're not all the way correct. Okay, let's solve these. All right, 4x subtract 5 is greater than 8. Divide by 4. X is greater than 2. Subtract 5. 4x is less than negative 18. X is less than negative 18 over 4. So x is less than negative 9 halves. Right, and that is negative 4.5. Okay, now we graph. And for me, when you make these graphs, you only need two numbers. Right? You're going to need the 2, and you're going to need the negative 9 halves. Make sure you got them in the correct relative positions. Right? Negative 9 halves is less than 2, so I put it to the left. Okay, how do I graph x is greater than 2? Open or close circle on 2. And because it does not have an or equal to, it is open. And then we have to add shading. Should I shade, if x values, which the shading represents, are greater than 2, which side of 2 do I shade? The answer is to the right. Okay, let's try this one. X is less than negative 9 halves. Okay, less than means open circle. And if it's less than that, on the number line, less than means to the left. So the answer, the solutions to this inequality are all the x values that are in this shading shaded area and this shaded area. Right? Now, could one value be both places? The answer is no. That's why it has to be an or. It's either these values or it's these values. So we have to tie these two different inequalities together with an or. Okay, let's try another one before I have you do a you try. What do I have to do to this one before I break down the inequality? Okay, the answer is I got to isolate the absolute value, right? You don't distribute the 2, right? You divide both sides by 2. You never want to do algebra with numbers that are outside the absolute value and inside the absolute value. Okay, now that we're isolated, we move on to the next step. We're going to write 2 different inequalities. Okay. Again, our expression, either our expression is greater than or equal to 6, or it's less than or equal to -6. Solve. Subtract 4. X is greater than or equal to 2. Subtract 4. X is less than or equal to -10. Right. And graph. Right. You don't have to put anything on this graph except for the 2 numbers, -10 and 2. Okay, what kind of circle am I going to use on 2? Closed, right, because it's or equal to. Which side am I going to shade if it's x is greater than or equal to 2? To the right. X is less than or equal to 10, closed circle, and it's less than on a number line, that means to the left. Right, so that's always what an absolute value greater than looks like. Right, it's covered the ends of the number line and it's open in the middle. So you go ahead and try this. Right, hit pause, and when you're done, hit play. Okay, this one is already isolated, so I can just write my 2 inequalities. Right, remember, don't include absolute value symbols at this point. Together, these 2 inequalities are saying the same thing without using absolute value symbols. And now we can do algebra with this. So subtract 5. X is greater than or equal to 5/3. Subtract 5. Divide by 3. Graph. Okay, if it's or equal to, it's closed circle. Since it's greater than, it's shaded to the right. Or equal to means closed circle, shaded to the left. I think I've got another you try here. No, I don't. Okay, now we're going to move on to the absolute value less thans. Okay, and that includes less than or equal to. Okay, just isolate the absolute value expression is still the first step. Second, rewrite the expression as one 3-part inequality without absolute value symbols. Right, this is going to be a hard thing for some of you to get the hang of, but 3-part inequalities are part of math. Right? If you look and see how the solution's done in the book, they're going to be using a 3-part inequality. And increasingly, as you move up the ladder here in math classes, 3-part inequalities are just how we do things. So you need to get used to it. Right? Then we're going to solve that 3-part inequality, which has a variable in the middle part of it, by doing operations to all three parts, and then we will graph it. Again, this may sound a little foreign to you at this point, but when you see it, it'll make a little more sense. Again, if you need more time copying the slide, then hit pause. Solve and graph. Okay. First of all, this one, the absolute value is already isolated. So what is this telling us? It's telling us that the absolute value of this expression has to be less than 6. We know that that means to the left of 6. So our expression has got to be less than 6. But here's the thing. If our expression has a value which is in between -6 and 0, what happens when I take the absolute value? Well, it's going to flip its sign so that it's in between 0 and 6. So it would be okay for our expression to have values anywhere between 6 and -6. Right? It can't be less than -6. If you take the absolute value of -7, let's say, you would get 7. And that's not less than 6. So we know that our expression has to be both greater than -6 and less than 6. So we write that as a three-part inequality. -6 is less than x plus 2 is less than 6. Okay, that's a three-part inequality. It's kind of two different inequalities tied together with the word and. I mean, that's telling you that x plus 2 is greater than -6 and x plus 2 is less than 6. It's got to be both. It can't just be one. But we're not going to write this using two different inequalities. We're going to write it with a three-part inequality. Now we have to solve for the variable x, which is in the middle part, right? And x is not alone. We've got to get rid of this plus 2. We're going to subtract 2. But since this is a three-part inequality, we have to subtract 2 to all three parts. Now we get -8 is less than x is less than 4. Now, if you set this up with two different inequalities and solve it, you must use the word and. And then when you graph it, you got to make sure that you are showing the solution as including only those values in between -8 and 4. Right, so I'm not saying that you can't do this with two different inequalities. You can, but I don't want you doing that. I want you using a three-part inequality. And if you insist on going your own way on this, that's fine. But if you don't get it exactly right, don't expect a lot of partial credit. That's what happens if you don't take my advice. Okay, so let's solve and graph this one. Okay, first, what do we need to do to this? Well, sorry, this is a you try. So before you go off, what are you going to do to this as a first step? Isolate the absolute value. Okay, so go ahead and do that. Hit pause, do the problem, hit play when you're ready to go. -3 on both sides. Now we've got 2x plus 1 is less than or equal to 9. Okay, now we've got it. Isolated absolute value is less than or equal to 9. We write it as a three-part inequality. -9 is less than or equal to 2x plus 1 is less than or equal to 9. Right? The value of that expression has to be in between -9 and 9. Now, to find which values of x satisfy that, we need to subtract 1 from all three parts. -10 is less than or equal to 2x is less than or equal to 8. Divide by 2. Now we have -5 is less than or equal to x is less than or equal to 4. And if we graphed it, we would have negative 5 on the left, 4 on the right. Because both of these are or equal to, we need closed circles. And the shading, x is clearly in between negative 5 and 4. Okay. 20. So here's another you try. So hit pause, and when you're done, hit play. Okay, this absolute value is isolated, so I can go right to the three-part inequality. Negative 4 is less than or equal to 7 minus x is less than or equal to 4. Solve for x in the middle. Subtract 7. So we have negative 11 is less than or equal to negative x is less than or equal to negative 3. Okay, that we have not solved for x yet. Right? We got negative x, we don't have x. So how do I turn that negative x into an x? Okay. You might say divide by negative 1, and you wouldn't be wrong. But you could also say you multiply by negative 1, and that's the multiplication property of negative 1. That is what I would do. Right? Multiply the whole thing, all three parts, by negative 1. Okay, now you got to remember, what happens to an inequality when you multiply it by a negative number? And the answer is, it flips the direction of the inequality signs. So negative 1 times negative 11 is 11. That less than or equal to becomes a greater than or equal to. The negative x becomes an x. And then another greater than or equal to. And 3 becomes a 3. And if you prefer, you could rewrite it as 3 is less than or equal to x is less than or equal to 11. So remember that one thing, you've done this before in Algebra 1. If you multiply or divide by a negative, you flip the direction of the inequality symbol. For a three-part inequality, you flip them both. Okay, here's my graph. Sorry, this is getting long. And they were both or equal to, so I have closed circles, and now I'm going to shade in the middle. So absolute value less thans always look like that. Right? The ends of the number line are not included, and the middle of the number line is. If you remember when we did the greater thans, it was exactly the opposite. Right? The middle of the number line was not included, and the ends of the number line were. Sorry, I'm just checking on something here, because I don't see my recording thing.
Hey, I think I just sent something to your printer.
Yeah, come on in.
Did it just print?
Yes. I'm making a recording. Okay, couple word problems before we're done. A professional baseball should weigh 5.125 ounces with a tolerance of 0.125 ounce. Write and solve an absolute value inequality that describes the acceptable weights for a baseball. Okay, so this is a tolerance means basically like error. I mean, if you tried to make, if you run an assembly line that's making baseballs, and you set the machine to say every one of these balls should weigh 5.125 ounces, do you think every ball weighs 5.125 ounces? No, it may be close, but it's not always going to be exact. So in the manufacturing world like this, you have to, set what is acceptable. Is 5.5 okay? Is 6 okay? Okay, what they're saying is the tolerance, the distance from the target weight, can only be 0.125 ounce. Looking at that on a number line, right, that means 5.125 is the middle. That's what we're aiming for. And the tolerance is how far to each side can you go. And you can go 0.125. Okay, well, what would 5.125 plus 5.125 be? That would be 5.250. And if I subtracted, that would be 5. Okay, the way you write that with absolute value symbols is you're going to say the absolute value of the weight of the baseball, let's use W to be our variable, minus the target is less than or equal to 0.125. Right. That's how you write an absolute value. With absolute values, this concept of tolerance, and I'm going to say like in a manufacturing setting, but it could be in other settings, I imagine, too. Okay, now once you've set it up, you could solve to find the acceptable weights. We've actually already done that, right? It's a three-part inequality. Negative 0.125 is less than or equal to W minus 5.125 is less than or equal to 0.125. Now we're going to add 5.125 to all three parts, right? And that is going to give us 5.0 is less than or equal to W is less than or equal to 5.250. Okay, similar problem. And these are examples in the book if you wanted to look at their pictures. Right. The thickness of the mats used in the rings, parallel bars, and vault gymnastics events must be between 7.5 and 8.25 inclusive. Write an absolute value inequality describing the acceptable mat thickness. So let's see, it can be in between 7.5 and 8.25. Okay, if those are the ends of the interval, then what do we need to be able to write this as an absolute value? We need the middle of the interval, right? How do you find the middle of that interval? Well, you add them up and divide by 2, right? What is 15.75 divided by 2? That'll give us, goes in 7.8. 0.75. So the middle is 7.875. Okay, that's telling us the middle, like our absolute value, the mat thickness, I'll call it T for thickness, is going to be subtracting the middle. Right? And it's got to be less than whatever is this distance right there, or this distance right there. Okay, well, let's see. It's probably easiest to subtract. What's 7.875 minus 7.5? Looks like 0.375. Now, is there any point solving that? The answer is no, because we already know the answer. The answer is 7.5 is less than the thickness is less than 8.25. But this is how that relationship is represented with absolute value inequality. Okay, there's 2 homework problems that deal with those kinds of word problems, so I wanted you to see that. Okay, I'm going to hand out a worksheet now which has got all the properties that we're just kind of using implicitly here and reminding you about the sets of real numbers. I don't intend to do like a whole unit on that or a whole section on that because they just don't have time in the curriculum. But I suggest that you put these in your notebooks. They're already 3-ring binder punched holes. Okay, and we went over these at the beginning of the lesson. These were our objectives, and we learned how to solve one variable absolute value equations and inequalities, and I gave you some properties and a review of the real number system. The homework is here. Now remember, odd number problems have answers in the back of the book. So look in the book and see that you can find those answers, because the odd number problems you should be checking on your own. The even numbers you won't have, I'll go over those at the beginning of the next class. Right? This is due at the beginning of next class. If there's any time left in this class, and there's probably not because this went on too long, you could have worked on your homework. Otherwise, just do your best. Most of them are fairly easy. You know, the word problems at the end, if you aspire to be an engineer or any kind of scientist, you know, engineers and scientists do word problems, right? You can't avoid them forever. So please do your best on those. And they're paired, you know, for every problem you do that's even and you don't have the answer, you had the one that was really similar that you did have the answer. Okay, so good luck on the homework, and we'll be checking that next time.